Okay, we have a couple of reactions left for aldehydes, and these are specifically for aldehydes in this case. And there's two special oxidations that only occur with aldehydes, not ketones, esters, carboxylic acids, acid chlorides. These reactions only occur with aldehydes. And the first one is called the Tollens test. Or the Tollens oxidation. Now, in the Tollens test, what happens is that if you take your aldehyde and you react it with, in this case, silver ion, and there's usually complexed with ammonia under basic conditions, the aldehyde will be oxidized to a carboxylic acid. And since this is a basic solution, the carboxylic acid will become deprotonated. So we make the carboxylate salt. And then later, if we wanted to isolate that, we could then say, add acid to the mixture to form the carboxylic acid. But now, this test is actually what's called a qualitative test for aldehydes, meaning that it gives a visual signal that we have an aldehyde present. And that doesn't come from the carboxylic acid. Instead, it comes from the silver. So as the aldehyde is oxidized, and remember it gains an oxygen here, the silver is reduced. And so from general chemistry, silver reduced means it gains an electron, and so we also get out of this mixture silver metal. And that's actually how we can tell that our aldehyde has been oxidized, is by this presence of this silver metal. Now, there's many videos online that you can look at. I've chosen one here that I'm going to go ahead and play for you. But before I do that, I'm going to go ahead here and talk about the other oxidation, then I'll show its video for the Benedicts test. And the Benedicts test is also specifically for aldehydes. It doesn't react with anything else, alcohols, ketones, etc., etc. So in this case, the Benedicts test, if you take an aldehyde, in this case, you're going to treat it with copper 2+, and this is usually under basic conditions again. So we're going to oxidize that aldehyde to a carboxylic acid, but since it's under basic conditions, that'll become deprotonated. And then the copper in this case actually gets reduced to copper 1. And that copper 1 then reacts with the oxygen, with the oxide ion to produce copper oxide, copper 1 oxide. And it turns out that this has a brick red color, so you end up forming a brick red precipitate. And the reason I call this brick red is that copper oxide is actually what's the pigment that's used to make bricks red, so therefore that's why it's a brick red precipitate. So again, the presence of this brick red precipitate indicates that you have an aldehyde and nothing else. It won't react with alcohols or carboxylic acids or ketones. And again, there's another video that I'll show you here for that reaction. Now, these reagents are normally used in sugar chemistry. And the Benedicts test in particular is a test for what are called reducing sugars. And the reason that they're called a reducing sugar is that it has a free aldehyde in its open chain form, and that free aldehyde can reduce either copper or silver, so that you see positive tests. Well, they've used a couple in here. Glucose is a reducing sugar. And what that means is, remember, there's an equilibrium between the cyclic, in this case, hemiacetal form of the glucose and its open chain. And in its open chain, we have this free aldehyde that can then react with either the silver or the copper. Now, a non-reducing sugar would be if you took two glucoses together and you actually formed an ether out of them. So in other words, we have the formation of this ether linkage, so those OHs disappear. When you have two sugar molecules that are connected by this ether linkage, they cannot be in equilibrium with their open chain forms, and therefore there's no free aldehyde to react. So maltose is not a reducing sugar, and you will not see a reaction of maltose with the reducing sugars tests, either Benedicts or Tollens. Sucrose, which is our table sugar, is a mixture of glucose and fructose. It also has this linkage, and so there is no open chain form aldehyde of the sucrose in order for it to react. So sucrose also gives a negative test. So you have to use glucose or dextrose and to give the positive test. So in these videos, when you see them use these sugars, D-glucose is a reducing sugar because of the presence of the free aldehyde right here at this in the open chain form. So let's go back here and let's look at the Tollens test first. Continue recording, and here is the Tollens test video, and their audio is going to play here.
This is just the Tollens test for reducing sugars on a large scale, but the resulting silvered flask is most impressive. The quantities here that we're going to use are appropriate for a 1 or 2 litre, 1 or 2 cubic decimeter flask, but they can be scaled up or down as appropriate. The most important thing to remember about this experiment is the flask must be scrupulously clean if we are to get a good silver mirror. The best procedure is to clean it with detergent and a brush, rinse it out with water, followed by concentrated nitric acid, and then several rinses with distilled or deionized water. We start with 150 cubic centimeters of 0.1 moles per cubic decimeter silver nitrate solution. We add to this, a drop at a time, some 8-HE ammonia. We get a brown precipitate first, which, on adding more ammonia, will eventually redissolve to give a clear solution. It'll take about 5 cubic centimeters of 8-HE ammonia. We now take 75 cubic centimeters of 0.8 moles per cubic decimeter potassium hydroxide. Again, we get a brown precipitate of silver oxide, and we add more 8-HE ammonia to this, a drop at a time. Again, until the precipitate redissolves to give a clear solution. This solution is ammoniacal silver nitrate. It contains silver plus ions complexed with ammonia molecules. We now put the ammoniacal silver nitrate into the flask we're going to silver. And add to it 12 cubic centimeters of 0.25 moles per cubic decimeter glucose solution. Glucose is a reducing sugar and will reduce the silver ions to metallic silver. The solution will start to go brown or grey, and at this point it's important to keep moving the solution around the flask so that the whole of the inside of the flask is constantly being wetted. Over a period of a couple of minutes, a silver mirror will begin to form on the inside of the flask. Stress, it's vital to keep the solution moving around so that the whole of the inside of the flask is exposed to the silvering solution. The chemistry of this process was actually used in the past to form the silver coating on mirrors, looking glasses. A giant Christmas tree decoration. When you finish this demonstration, it's important to dispose of the spent ammoniacal silver nitrate solution as quickly as possible. You should do this by pouring it down the sink and flushing it with plenty of water. Ammoniacal silver solutions have been known to explode if they're left standing for some considerable time, for example overnight. Therefore it's vital not to put the residues in a silver residue container. For the same reason, it's not appropriate to make up the ammoniacal silver nitrate solution any considerable time before the demonstration, and certainly not the previous day, for example.
So there is the Tollens test, and now we will look at the Benedicts test. And this goes into a little bit more of the reaction details, but you can take a look at this.
Benedicts test. By the end of this exercise, the students should be able to distinguish between reducing and non-reducing sugars using the Benedicts test, outline the process, and also write a well-balanced reaction equation for the test. Benedicts test is a test for reducing sugars. Heating a mixture of Benedicts reagent and a reducing sugar such as glucose leads to the reduction of the cupric ions in Benedicts reagent to cuprous ions with the formation of copper 1 oxide, seen as a yellow to red precipitate in the mixture. The materials used in this test procedure are maltose, glycine, Benedicts qualitative reagent, glucose. You may also need a pipette, test tubes, and a measuring cylinder. Pipette 1 ml of each test solution into labeled test tubes. Add 5 ml of Benedicts qualitative reagent.
Notice that the color of the copper solution, the copper 2, is that is the blue color that signifies
Heat
that it's
all
copper
the test
2.
tubes containing the mixture in boiling water and heat for 3 minutes. Cool and observe. Glucose, a reducing sugar. Maltose, a reducing sugar. Glycine, a non-sugar. On prolonged heating, maltose would hydrolyze into glucose to yield a positive result.
So let's stop that for a second so it doesn't look like we're contradicting my results. the maltose only reacts because upon heating it hydrolyzes apart to form the glucose. So you can see that the color is not nearly as intense as it is for the glucose because only part of the maltose has actually broken apart, and then only part of that has actually reacted. Glycine is an amino acid, so it's not, it has no aldehyde to oxidize. So the maltose here, even though it does give a slightly positive, it's because it's hydrolyzing to form glucose. Okay, so those two reactions are specific for aldehydes. Nothing else is oxidized by using either silver or the copper reagents. Okay. Now, last reactions of aldehydes and ketones are the reductions that we've seen in the past. So if I take, for instance, an aldehyde and I react it with sodium borohydride and then add H plus H2O to that, what do I get? What would be the same reaction if I took the ketone and reacted it with sodium borohydride? Well, remember that the aldehyde would be reduced down to a primary alcohol, and the ketone would be reduced to a secondary alcohol. Now, also remember that when we took acid chlorides and did Friedel-Crafts acylation reactions and put the carbonyl group on the benzene ring to make our phenylketones, what reagent did I use to reduce those? And more importantly, I reduced those down to completely the CH2 group. So what two reagents could I use here? If you said de Wolf-Kishner, which was what reagent? N2H4, KOH, and heat. And then, or number 2 was Clemenson. Clemenson was, if you said zinc, mercury, HCl, and heat, then those were the two reductions that we had, but they were complete reductions of the phenyl ketones all the way down to the CH2 groups. Okay, so that kind of ends the reactions of aldehydes and ketones, but I skipped ahead at the beginning of the chapter all the preparations of aldehydes and ketones because it made sense to talk about hydrates and acetals and hemiketals and imines and enamines, because now we can go back and we can begin to understand a little bit more some of the ways to prepare aldehydes and ketones now that we know about the acetals, hydrates, and imine chemistry. So, how do you synthesize aldehydes and ketones? And these are new methods, not the old ones that we had for review a few lectures ago. So in terms of the first method is to use what's called a 1,3-dithiane. A 1,3-dithiane has two sulfurs attached to the same carbon. And this sulfur, basically you can think of this being taking this molecule and reacting it with formaldehyde to give you this dithiane molecule. That's a little more difficult than that, but this dithiane in essence would be sort of the equivalent of, well, it'd be the sulfur equivalent of ethylene glycol in terms of forming a, in this case, what's called dithiane. which is almost a protected formaldehyde. So what we do first is that we use an alkyl lithium, such as, let's say, the butyl lithium that we used in the Wittig reaction. And I'm going to use this butyl lithium to deprotonate one of the two hydrogens on the dithiane to make this carbanion. Then I take this carbanion and react it with a primary alkyl halide. And it has to be primary here because this is still a C- and a fairly strong base. Not only that, but it's kind of sterically hindered. So we still have one hydrogen attached here. But what would happen then is I do that SN2 reaction to then kick off the halogen leaving group. And what I've done is I've done an alkylation reaction to form what's called a thioacetal. So if you think about the terminology here, this came from an aldehyde originally formaldehyde, and it's got the thiane, so this is called the thioacetal. And really you can think of this as being a protected, it's basically a protected aldehyde. So if I wanted to, I could deprotect this using acid and water. Now people throw in the mercury because mercury has a very large affinity for sulfur, and so the mercury will help pull the sulfur off of this molecule so that I would end up with the SH groups bound to mercury, but then this helps hydrolyze that or deprotect this now aldehyde. And so what I've done is I've started with dithiane, and I can put any alkyl group onto that as long as it's primary. So the restriction here is that we have to have a primary alkyl group as our aldehyde. Okay, so you can say, well, couldn't I do that again? And the answer is yeah, you could do that again. So we could go through this series of reactions to begin with, put one alkyl group onto the, make the thioacetal out of the first alkyl group, and then we could simply deprotonate this hydrogen to form another carbanion, and then go ahead and react that with a second alkyl group. It doesn't have to be the same as the first. That's why this is R prime and this is R double prime. So now I can make a thioketal. And so then I could deprotect the thioketal to give me the ketone now. And so I can basically, using this synthesis, I can decide, okay, I want to make a ketone and I want to put this alkyl group and this alkyl group onto that ketone. And so going through that, I could do that. Now, the big limitation here is that both the R prime and the R double prime, they end up having to be primary. But outside of that, we could make a variety of different ketones using the thioacetal, followed by making the thioketal and then deprotecting that to form a ketone. So that's one new method that, had I shown you this a couple of lectures ago, wouldn't have made much sense, but hopefully now it makes sense because you look at this and go, oh yeah, that's just protected formaldehyde, this is a protected aldehyde, this is a deprotected, or this is a protected ketal, and so then we deprotect to form the ketone. How else can I make ketones? Well, we can use carboxylic acids to make ketones using Grignards. Now, the last time we talked about this topic, in a way it was kind of a trick question, because had I have given you this reaction, what would you have written? Well, you would have noticed that this is a carboxylic acid. It would have been deprotonated by C-, so we would end up forming in this case, the lithium would be the counterion for the carboxylate, and we would have formed CH4. Well, now what I'm going to do is now I'm going to add a second equivalent of Grignard to this. So the first step can either be done with the alkyl lithium. So I can do this with two equivalents of alkyl lithium, or a lot of times people will use lithium hydroxide for this reaction. But either way, I'm going to form the lithium carboxylate salt. Now, once I take that lithium carboxylate salt, what am I going to do? So after we've deprotonated the carboxylic acid, then what we would do is, then I'm going to add a second equivalent of the organolithium compound. Now in this case, the second equivalent is going to attack the carbonyl so that it basically, the product will have two O minuses. And there would be lithium counterions to go with this. So at this point, we're done. We can't add any more nucleophiles because we don't have a carbonyl to add to. Now, what we would do is then we would add our H plus H2O step. And when we do that, what do we form? And this is why I didn't talk about this a few lectures ago, because now we form this molecule if we protonate both of those O minuses. And this molecule is called, hopefully you said, hydrate. What do we know about hydrates? Hydrates are unstable. And so this would immediately rearrange to form the ketone. So the reason that I didn't talk about this a couple of lectures ago was simply because the ketone, or because we didn't know about hydrates. And so now if you know about hydrates, you say, okay, well, we deprotonate the carboxylic acid in the first step. We then force the CH3 or the Grignard to add to the carbonyl in the second step. Then when we protonate these two O minuses, we form a hydrate. We know hydrates are unstable, so therefore it's just going to revert back to the ketone. So the overall goal here is that you can form a ketone and add an R group from that ketone, from the Grignard, by reacting a carboxylic acid and two equivalents of the Grignard, or a combination of lithium hydroxide and the organolithium. So that's another new way to make a ketone from a carboxylic acid. Okay, can we make ketones from nitriles? Well, this nitrile we saw, the C triple bond N. This also involves doing a reaction, that we only saw a few lectures ago. So we have to realize what the C triple bond N is, that the C is delta plus, the N is delta minus. If I react one equivalent of a Grignard with this, what happens is the R minus comes in, attacks this carbon, pair of electrons go off to the nitrogen. So what does that make? Well, that means I have a nitrogen now with two lone pairs and a negative charge, and then this R in this case is the alkyl group from the organolithium. So at this point, I'm done. And when I add an H plus to this, what do I form? Well, my N minus is protonated, and I end up with this. What is that? If you said that is an imine, you are correct. What do we know about imines? Imines aren't stable. So what do imines form? Well, this imine came from a ketone and NH3. And so again, the equilibrium lies towards the formation of the ketone, so that In this case, that reduces itself or reverses itself, so that once I form the imine, I end up with a ketone. Notice the net result here. The net result is that I can synthesize a ketone if my one R group comes from the nitrile and the other R group comes from the organolithium. And so I can synthesize a ketone using those two functional groups. We know how to form organolithium compounds. Simply take an alkyl halide, react it with lithium metal. How do you form nitriles? Well, a nitrile would probably be easily formed by taking your alkyl halide and reacting it carefully with cyanide ion. That would come in, do an SN2 reaction, and form our nitrile that we could then go ahead and react with the organolithium. So we can make both a nitrile and an organolithium. So that's both of those are easily synthesized. Again, this reaction doesn't make much sense unless we know about the imine and we know that the imine is unstable, so that it just breaks apart to form the ketone. Okay, now how about reduction of acid chlorides? We know this reaction. We took carboxylic acids and said that if you wanted to reduce a carboxylic acid down to a primary alcohol, you needed to use lithium aluminum hydride. Now we can talk about the mechanism of this. Remember that lithium aluminum hydride, like sodium borohydride, is a source of H-. There are 4 H- in each mole of lithium aluminum hydride. So let's take our carboxylic acid and react it with H- number 1. What's going to happen? If you said you're going to deprotonate to form the carboxylate and form hydrogen gas, good. That's the first equivalent of H-. What's the second equivalent of H- now do? Attack the carbonyl. So now what do I form? I form this hydrate, or once I form this dianion, next couple steps are kind of, let's call them magical. Because there's no H+ in this mixture. And so what happens is that our dianion here, we know that if it became something like this, we know that if these O- picked up a hydrogen, it would form the hydrate, and then that hydrate would become an aldehyde because the equilibrium lies towards the formation of the hydrate, because the hydrate's unstable, so the equilibrium would move towards the aldehyde. And then my third equivalent of H- is going to do what? It's going to attack that carbonyl, so that I'm going to end up forming my alkoxide ion. And now then I would have my then H+ H2O step, so that I would end up forming my primary alcohol. I have to say that this step right here is probably the most difficult to imagine, but this is a pretty strong base, and so it would pick up an H+ from wherever it could, from the solvent, from trace amounts of water. I would think in this reaction you would want just a little bit of water present in order to form the hydrate, but not enough water to actually form, let's say, to form the alcohol. So that's a step that's always confused me, but this is just pretty much how we can explain how the reduction of the carboxylic acid to the primary alcohol goes. And if it looks familiar, it's because pretty much these first couple of steps here are the same thing that we just saw for reacting Grignards with carboxylic acids. Okay. What if you wanted to take a carboxylic acid and maybe stop at an aldehyde? Well, that's not as easy to do. And so one of the ways that people have come up with to reduce, to take a carboxylic acid down to an aldehyde isn't to use that, but to use the acid chloride. Now, here's my carboxylic acid chloride. And the carboxylic acid chloride, if reacted with either lithium aluminum hydride or sodium borohydride, would be reduced all the way down to the CH2OH. So to go all the way down to the primary alcohol. I mean, that much we know. If I wanted to stop at the aldehyde, what I have to do is I have to use a less potent reducing reagent. So a less reactive H- source is this reagent where I've replaced 3 of the hydrides with terse butoxide ions. And this is called tri-terse butoxy lithium aluminum hydride. Notice I have a single H- here, and so this reagent is a lot less potent a reducer. So if you take a look at this, here's what would happen in this mechanism. So we take our acid chloride, and we now react it with the H- from the tri-terse butoxy lithium aluminum hydride. The H- comes in, adds to the carbonyl, and we end up forming then this alkoxide ion. Now, that alkoxide ion says, you know, if I could bring this pair of electrons back down here, I'd reform the carbonyl. In this case, there's a chloride ion that could leave, and so if it does that, it's going to kick off that chloride, so I'm going to end up losing Cl-, and then I form my aldehyde. And so if there's only one hydride and the reagent isn't very active, then we can end up doing this substitution. This would be a carbonyl substitution of an H for a Cl, and we'd end up stopping at the aldehyde. Now, on the other hand, if this was lithium aluminum hydride, then after I formed this aldehyde, so if I had LiH4, I would have a second H- that would then come in, react with that aldehyde, and I would end up forming then my alkoxide ion, and then add my H+ at the end to fully reduce that acid chloride down to this primary alcohol. So by using the lithium terse butoxy aluminum hydride, that gives us the chance to stop at the aldehyde. But this first step of addition and then substitution would then be followed by another H- adding. So we can make aldehydes out of carboxylic acids, but what I would first have to do is to take my carboxylic acid and convert it to the acid chloride and then react it with the tri-terse butoxy lithium aluminum hydride. How would I accomplish this reaction? If you said SOCl2 or something like PCl3, you're correct, because that's how I replace the OH with a Cl. Okay, so we can make aldehydes out of acid chlorides. What happens when you react an acid chloride with a Grignard? Well, I'm going to react it with 2 equivalents of Grignard. We actually saw this reaction before. We reacted acid chloride or ester with 2 equivalents of Grignard. But now we can understand the mechanism for this. So if I take my acid chloride and I react it with my Grignard, what's going to happen? The R minus is going to attack this carbonyl. I'm going to do my addition, and I'm going to end up with my O minus, and then my alkyl group having added to the carbonyl carbon. What happens next? Well, if you said this pair of electrons can move back down here, kick off the chlorine, you're correct. So I'm going to end up losing Cl minus to then form my ketone. Well, if you added only one equivalent of Grignard to an acid chloride, you would get a whole mixture of products, because if you formed a ketone, then some of this Grignard could react with that ketone. So that's why we just use two equivalents. And now the second equivalent of Grignard is going to react with this ketone the same way it did many, many months ago. So now I'm going to form my tertiary alkoxide, where now two of the R groups came from the Grignard, and now that just waits for a then H plus H2O step to occur, so that I form my tertiary alcohol with the two alkyl groups adding to the carbonyl. So now we're just looking at the mechanism here, and I'm beginning to introduce the idea that we have substitution occurring when I'm reacting, number one, a carboxylic acid derivative, not an aldehyde or a ketone, but now I'm reacting a derivative, and now I'm substituting my R group for my Cl minus. Okay, if I wanted to take that acid chloride and stop at the ketone, what would I do? Well, we saw earlier that what I needed to do if I wanted to take the acid chloride down to the aldehyde was simply use a less reactive hydride source. Kind of think of that here. I want to use a less reactive organolithium. Turns out that the lithium cuprates are less reactive, and so in this case this less reactive one would be to react the lithium cuprate with the acid chloride. Since this is going to end up being less reactive, I'm going to end up just adding the alkyl group to the carbonyl. And again, your R minus would come in and add, and then your O minus comes down and kicks the chlorine off to form that ketone. But in this case, it's less reactive, and it only adds one carbanion to that acid chloride. And that's just one of the ways that lithium cuprates are different than organolithium compounds. So we have a number of different methods that we could use to make ketones and aldehydes, and from acid chlorides or from the reductions. And they're all just kind of different plays on the reactions that we've already seen. Okay? So that ends the aldehydes and ketones chapters of the text. And so now we're going to take a little bit of a diversion here through amines in chapter 19, and then come back and talk about carboxylic acids and their derivative reactions after that. So just the basics of amines for the last few minutes of this lecture. So for common names of amines, first of all, an amine has a nitrogen atom, and that amine could have 1, 2, or 3 alkyl groups attached to it. If it has one alkyl group, it's a primary amine. If it has 2 alkyl groups, it's a secondary amine. If it has 3 alkyl groups, it's a tertiary amine. We've already seen that primary amines and secondary amines react differently with ketones to form either imines or shift bases, or secondary amines form the enamines. So there is a difference here. As far as naming and coming up with the common names of these amines, basically you're just going to name the alkyl groups that are attached to the amine. So for instance, if you had, I don't know, something like this would be, in its common name, this would be cyclohexylamine. You could end up with diethylamine. Or commonly, a common one might be something like triethyl or trimethylamine. So we just name the alkyl groups that are attached to the nitrogen. Now there are some others that one can get into. If you take, for instance, and add an NH2 to a benzene ring, this is aniline that we've seen earlier. If you take and put the nitrogen in a ring like a heterocycle, this is called pyrrolidine. If you remember with the two double bonds here, that was called pyrrole. This is pyrrolidine. And the six-membered ring is called piperidine. So you can also have common names of those reagents as well. Now the aniline, and then I'll add one more here because this one we've seen before. If you have the nitrogen as part of the aromatic system, this is pyridine. And pyridine we had seen earlier, because if I take my pyridine and I add HCl to it, I form pyridinium chloride. And if I add chromium trioxide to that, then I form PCC, which was pyridinium chlorochromate. And there were lots of nitrogen compounds, remember, in the heterocycles that we talked about when we were talking about whether something was aromatic or not. Also remember the idea that when you do have an aromatic system, if the lone pair is outside of that, then the nitrogen is basic. If the lone pair, for instance, in the case of the pyrrole, that if the lone pair was part of the aromatic system, then the lone pair was not available for bonding an H+, so in this case, that nitrogen was not basic. But on the other hand, this nitrogen right here is basic because it's not part of the aromatic system. Now, it turns out that the rest of these, all of these nitrogens, all the nitrogens in these compounds turn out to be basic in all three of these. We'll talk about basicity here in a moment or two. Okay. So that's the common name system for the amines. Now, if we talk about IUPAC naming, the IUPAC naming is a little bit trickier in terms of it's similar to what we have for alcohols, except the problem here is it's more similar to the it's more similar to the ethers, except you can have 3 groups attached to nitrogen, so we have to be able to handle this. So the first thing is, this is going to be named as an alkane. It's going to have the alkane, then the number, and then the word amine. So what do I mean by that? Well, for this molecule, this would be called butane 2 amine. That would be the new system of naming. So this is butane 2 amine. And when we look at the amine functional group, the carbon with the longest chain is going to become the parent name. So let's just take, for instance, that butane 2 amine, and let's add a methyl group to this nitrogen. How would I name this? Well, this is still going to be butane, not butane, butane. To amine. But now what it's going to have is we have to indicate that there's another methyl group attached to the nitrogen. And so the way we do that is we actually say, okay, this is a methyl butane 2 amine, but see, this is my longest chain right here. So I have to have a way to indicate that the methyl group is not attached to the butane chain, but instead it's attached to the nitrogen. So we put an N in front of the alkyl groups that are attached to the nitrogen. So in this case, this is N-methyl butanamine. And so that indicates that the butanamine is the base, the parent, and that attached to the nitrogen, there is one methyl group. We could further expand on this and say, well, what would happen if I had, I don't know, if I had let's not do 2 methyls because, well, let's do 2 methyls on the nitrogen here. Let's do 2 methyls on this nitrogen, and then I'll have 2 different groups. So looking at this, this is the group with the longest carbon chain, so this makes this again a butane 2 amine. Now I've got 2 methyls attached to the nitrogen, so I have to indicate that both of those methyl groups are indeed attached to the nitrogen. So what would come in front of this is an N and dimethyl, and then the butane 2 amine. So the nitrogens in front of the dimethyl say both of those methyls are attached to nitrogen, and then the butane 2 amine tells me that's what the base of the molecule is. So so when you have more than one group on the nitrogen, then you just have to say in this case it would be NN dimethyl. So looking at the nitrogen, then we're going to choose, just to go back and kind of summarize this, when you look at the nitrogen, the group with the longest chain is going to be the parent group. Now that sets the butane up, and then you use the prefix N to indicate what alkyl groups are attached to the nitrogens, or to the nitrogen atom. So what are some other things? Well, if you look at the aniline, now in this case, after checking with some other sources, this molecule actually, what we have is we have 2 groups that would give the benzene ring different names. It would either be a phenol or an aniline. And actually in this case, because the oxygen has the higher sequence, the higher ranking in the sequence rules, this would actually, in this case, be called either meta or 3-amino phenol would be its actual name. So we do actually use the Conn-Ingold Prelog sequence rules, and nitrogen doesn't. While it beats a carbon group, it doesn't beat an oxygen. So NH2, when treated as a substituent, is called the amino group. We can get into some other molecules. For instance, if we tie this back together with the idea of, this ketone, let's say I had this molecule. Since the ketone since the carbon with the oxygen beats the carbon with the nitrogen, this would have priority over the nitrogen in the naming. So we would number there. This is going to be from the last naming. This is going to be a cyclohexanone. And in this case, it's going to be an N-methyl 3-amino cyclohexanone would be its name. So again, we have an amine group at carbon 3. We have the N-methyl indicating that attached to that amino group is a methyl group, and then that's at carbon 3 relative to the ketone. Another example might be that if you had a cyclohexane with our aldehyde off of that, and you had, let's say, an NH2 group, maybe a bromine attached here, that if we're looking at this molecule, the carbaldehyde that we talked about before would have the higher naming priority, and then we would number so that we encountered the first substituent. So this would actually be called 4-amino, because amino comes first alphabetically, 2-bromo, and then we would call this cyclohexane carbaldehyde. Would be its name. So again, the C double bond O takes precedence over the nitrogen group. So if you have an amine group and you're going to treat it as a functional group, then you would want to give that the amino name. If it's just simply an amine that is the only functional group or has the highest priority, then we're going to look at the group that has the longest carbon chain as the base chain, and then we would name from there. Okay, so there's other basic naming in your book, but that's pretty much how we would name these amines. Okay, just to kind of finish out the idea of the structures of amines, and then I'll call it a day. When you have the structure of an amine, you have a nitrogen that is indeed sp3 hybridized, that has a lone pair in one of the hybrid orbitals, and then your 3 H's, or well, 1 carbon, 2 H's, or 3 carbon groups. There is sometimes an issue here about chirality of the nitrogen. So in other words, if I had 3 alkyl groups, it is possible to think about this in terms of stereochemistry, in terms of this forming a non-superimposable mirror image isomer, except the problem with nitrogen is that it actually undergoes what's called rapid inversion. So in this case, what would happen is the nitrogen could go from being sp3 to being sp2, with the lone pair in the sp2, so there'd be an equilibrium here. And then that could continue so that now the lone pair was in the bottom lobe, and we reformed our sp3 hybridization. And so this rapid inversion means that nitrogen atoms cannot be chiral. And I'm going to put an exception, or I'm going to put a rule for that in a moment. But a nitrogen cannot be chiral if it has a lone pair because of this rapid inversion. Now, that does not mean that you couldn't have a nitrogen that has 4 groups attached to it. So if you had an ammonium salts don't undergo inversion. So in this case, in the ammonium salt case, this could be chiral, and you could end up with enantiomers of that chiral ammonium. That is a legitimate possibility. And so you would basically just determine R and S configurations based on those groups. But it is possible to have an R or an S configuration for an ammonium salt, but not for a nitrogen with a lone pair. Okay, so there is a possibility of one form being chiral, but not all of the forms being chiral. Okay, all right, so we'll call it quits for this. I will post the online quiz, and then if you have any questions, bring them to class, or if I put the survey box online, then write the questions in. Otherwise, we'll look at these reactions in the class period for this lecture.